Wonderful. Thank you. Thank you for coming. And in Europe, it's already late evening. So I'm Alina, and I will talk today about modeling supercritical resource utilization. I don't know how to. Okay. So as Thomas just talked about, both the IDDP1 at Krafla and IDDP2 at Reykjanes have encountered supercritical conditions. And now there are plans to drill already IDDP3, but it is still not clear how to utilize the potential supercritical resource best, as Thomas just mentioned, whether it should be a direct production or injection into the resource, or maybe a combination of injection and production wells. So we dedicate our modeling efforts to explore this, and hopefully we can get some insight. And to do a modeling with a well, you need a well model. So we have implemented Pisman-like well model into our in-house simulator CSMP++ within the control volume finite element method. And as Thomas just presented before, pioneering work by Sam Scott was performed in 2D, and now Benoit and I, and Sam also later, we will present some of the first results using a 3D extension of this control volume finite element method. So why do we need a well model? Let's consider single phase flow near a single well, and in an isotropic porous medium. And assuming constant fluid properties, we get this analytical solution for the pressure near the well. It looks like this. And if we plot it here, I've plotted it here with a dashed line. And here on the x-axis is a distance from the well. And we see that pressure drops most dramatically in the immediate vicinity of the well. And that's why this is very difficult to capture with a numerical model without an extreme mesh refinement near the well. So this problem was discovered early on, and already in 1978, Pisman came up with a very clever well model. And this model has two key features. So one clever idea is that Pisman introduced two unknown variables for pressure at the well pressure and the reservoir pressure. And the use of these two unknowns allows us to capture this steep pressure gradient. And the second, and then further from the well, pressure curve behaves more nicely, and then you can approximate it with linear approximation. And the second key feature is so-called equivalent radius. And equivalent radius is the distance at which this numerical reservoir pressure variable is equal to the analytical pressure. And here on the right, there are some details of the how this well model looks in our 3D model. So we're using unstructured grids, and here a single well node is displayed. And at this well node, we have two variables for pressure, the well pressure and the reservoir pressure, and all the other neighboring nodes, they just have the reservoir pressure variable. And the effective radius is calculated from the mesh around the well node. And the one other important feature of this particular implementation is that it does not require any special configuration of the mesh near the well. So on the next slide, I just wanted to quickly show the main governing equations for the CBFEM, and just to mention the key features of the code. So it can model two-phase flow of liquid and vapor and boiling. We can model salt transport and heat transport in terms of enthalpy advection and the conduction of temperature. And the pressure equation is derived from mass conservation. So this scheme is locally mass conservative, and it is able to capture strong gradients in fluid properties that can arise right above the magma chamber. And the well model is right here. So this is the source term for the well. It's well injection or production rate, and the Piesman well model is within this source term. And the well is represented by a set of n nodes of the unstructured mesh connected by the edges between those nodes. And the wells can be operated either on the fixed rate or the fixed pressure control. And in this model, the flow in the well bore is not modeled. And Benoit will tell later about a more advanced well model which considers flow in the well bore. So we have implemented this model and we benchmarked it against the analytical solution. This is a very well-known benchmark case in oil and gas industry. It's called quarter of the 5 spot. And it's a 2D model, 1 kilometer size square. And we have 2 wells located in the opposite corners with fixed pressure conditions, a production well and an injection well, and temperature is 140 degrees C. And this analytical solution provides us the pressure difference between the injection and the production wells. So here on the left, the pressure distribution in the model is shown after the steady state flow has established. So first, let's look at this graph. So I have plotted the analytical solution for pressure near the injection well, so along this line here. And those other curves are the numerical pressure solution results without using the well model. So just applying the fixed pressure at the left corner and the right corner. And these simulations were done for 3 different meshes with varying mesh sizes, for average size of 25 meters, 50 meters, and 100 meters. And we see here that if we don't use the well model, we cannot capture this strong gradient in pressure near the well. And the numerical results are highly mesh dependent. And even like with the best resolution, we cannot capture this curve. And on the right here, I've plotted the results with using the well model, the Piesman-like well model. And we see that by using reservoir pressure, well pressure and reservoir pressure at those 2 nodes, we can capture the increase in temperature near the injection well, and the numerical results are much less mesh size dependent than without the well model. So with that, we now apply it to model supercritical resource utilization. But as Thomas has talked before, it's very important to do not to apply some artificial boundary conditions at the shallow depth, but to explicitly represent a magmatic heat source. So in this 3D model that is 5 kilometers deep and 10 kilometers in horizontal size, we model its fully transient geothermal system evolution from the moment of magma chamber emplacement. And the magma chamber is 3 kilometers in diameter, 1 kilometer thick, and the top of the intrusion is at 2 kilometers depth. And the initial temperature is 900 degrees C. And also this temperature-dependent rock permeability is a key feature in this model. And on the right, you see 4 snapshots of the geothermal system evolution. So after 1.5 thousand years, the system is in its incipient stage. So the magma chamber starts to cool and heat up the rock above it and initiates the geothermal convection, with where you have a single pipe-like upflow structure above the magma chamber and the downflow of cold groundwater in the middle. After 2.1 thousand years, the boiling reaches the surface, and this pipeline structure merges into a single upflow zone. And after 2.7 thousand years after the intrusion, the geothermal system has fully evolved, and the boiling extends all the way from the surface down to the intrusion. And after 3.2 thousand years, the system is in its veining stage. So the magma chamber is completely crystallized, but there is still boiling in the first 1 kilometer and underlain by the single phase fluid. So in the next two slides, I will show some 2D slices here through this 3D model. So as I said, the incipient stage of the geothermal system evolution, where the magma chamber has just crystallized just a little bit, and then after 2.7 thousand years, the magma chamber has substantially crystallized. We see the boiling that extends all the way from the surface to the top of the intrusion. And if we zoom in here in this area, we see that right above the current brittle ductile transition, where the rock already has become permeable again, there is an area where temperature exceeds the critical temperature of water, and fluid enthalpy is above 3 megajoules per kilogram, and the fluid is at single phase supercritical conditions. So this would be a potential supercritical resource that we will now target with a well and try to simulate. So first, let's look at the single injection well simulations. So the well completion is installed right in the middle here, between 2.1 and 2.2 kilometers depth. And this is the temperature and liquid saturation before the cold water injection. And here we inject cold water at 80 degrees C and a relatively low rate of 3.2 kilograms per second for 100 years. And what we observe is that the area around the injection well is progressively cooled down, and there is a sharp boundary developing between the single phase cold injected fluid and the single phase supercritical initial fluid. And we don't, in this case, we did not observe any mixing of the, or very limited mixing of injected cold and initial supercritical fluid. On this slide on the left, I have plotted the pressure near the injection well, and we see that the well model captures really nicely the steep gradient near the well, and also that pressure around the well is increasing with time with injection, which makes sense. And on the right, I have plotted the permeability along the vertical line through the middle of the model. So here's where the well is located, and I've plotted the permeability after 100 years of cold water injection, the orange line, and the green line is after 100 of natural system evolution without any wells. And we see that the cold water injection facilitates the crystallization of the heat source, and the depth of the brittle ductile transition is retreated further down. Next, we have modeled a case of a single production well, and this well is operated under fixed boundary hole pressure conditions of 100 bars. And here on the left, we see the temperature and the liquid saturation prior to production, and on the right, after 100 years of production from this well. And what we observe is that the temperature decreases near the well, but still is very high even after 100 years of production, and that after 100 years, the whole area near the well has fallen into two-phase boiling conditions, but also that the production affects the area up to 500 meters above the well, actually, and the liquid saturation increases in the area above the well. On the next slide, I'm comparing two production scenarios with a lower bottom hole pressure of 60 bar and a higher bottom hole pressure of 100 bar from the previous slide. And what we see here in this panel is that with a lower bottom hole pressure, we achieve a higher well rate, which also makes sense, but this comes at the cost of bottom hole temperature of the production well decreasing faster in the lower bottom hole pressure case. But what we also see is that the production temperatures stay very high for many years, which is very promising. And with 100 bars bottom hole pressure, on the boiling in the well starts only after 98 years or so. Another interesting finding is that the total thermal energy rate of the well is increasing with time, even though the enthalpy of the produced fluid is decreasing, but the mass rate of the well is increasing with time, and this overpowers the decrease in fluid enthalpy. And the well mass rate is increasing with time because the density of the produced fluid is also increasing with time. So already to the conclusions. Here I have presented some of the first simulations of utilization scenarios of geothermal wells tapping the potential supercritical resources. And what we saw is that the injection of the cold water into the supercritical area results in a progressive cooling of the region around the well. And our production well simulations suggest that superheated fluid production could be carried out for decades, which would, of course, make a big difference for the geothermal energy production. And just to give some outlook, in these results, so because those are only the first simulations, we have rather low well rates, and this is for two reasons. So one is that we have a very short completion length of the well, only 100 meters. And the second reason is that we have 10-15 square meters background permeability. So in the future, we plan to explore those the different permeability configurations and the longer completion rates, and also to simulate different combinations of injection and production wells. So with that, thank you very much for your attention.
Thank you, Alina. Excellent. Yeah, thoroughly absorbing presentation. Really enjoyed it. There's a few questions in the chat line that we can look at. There's three very active chatters, Tim, Jesse, and Helen. And I'll just read out those, and you can choose which ones you want to answer. Jesse asks, is there any conclusion on brittle ductile transition studies? Tim asks, does seismic delineate the loss of fractures? Then Jesse asks, have you ever tried combined finite element method and discrete element method? Tim asks, how close to the well do you need actual rock properties? And finally, have you identified any relationships between the changes in pressure gradient close to the well and drawdown? So there's a lot of questions there. If you want to answer any of them, you're most welcome in the next minute or two.
Yeah. So cannot answer the first two because I'm actually not a geologist or geophysicist. Have we tried finite element, discrete element method? No, we're using control volume finite element method. How close to the well do you need actual rock properties? This is something also for the future studies, and also there is this parameter in the well model that's called the skin factor that can take into account changes in the permeability in the damage zone around the well. So there is a positive skin and the negative skin, which one of this, like if you have stimulation near the well, and the other one if you have maybe clogged the porosity with drilling mud or something. So this is something still to explore. And have you identified any relationships between changes in pressure gradient close to the well and drawdown? Sorry, not sure I understand that actually. Yeah.
That's right. There was one new question about heat production from closed loops, injection versus production. Please
stay longer. Sam Scott will tell a little bit about this.
All right.
Using the same well model.
Okay, and I have one more question before we wrap up, and it's about the cooling I expect will be fracturing and changing the permeability with time. And is that incorporated in your model, the near wellbore model, the effects of the fracturing caused by cooling and changing the permeability and therefore the flow rate into the well? Is that incorporated in your simulator at all?
No, fractures at the moment are not incorporated, no.
Yeah.
And
so I guess that's the challenge, isn't it? Transient permeability. How do you incorporate it into your simulator?
Yes, but we're working on it, so it will come.
Excellent. Okay, well, thanks very much once again for that, and we'll wrap that up and move on to the next presenter.